Today I'm going to be going over Goodbye 2020. Uh, at least I'm going to be going over A through G. I wasn't able to solve H or I. Let me know real quick if people can see and hear me clearly. I just want to make sure my computer stuff is working okay. Okay. And thanks everyone for the follows. And just to check something, when people follow, you don't hear a chime, right? Only I hear that. Wait. Um, yeah, before I solve the problems, I just want to make sure my setup is okay. Okay, cool. Um, okay, perfect. Yeah, so there should just be little notifications here when people follow, but but no sound. Okay, perfect. Just because I want people to be able to hear the actual content. And let me unmark my stream is finished on Codeforces. Um, cool. So I guess I should get started now with A. Hi everyone. Um, cool. I'm slightly confused about one. Okay, I guess I'll get started. Was this contest rated? Yes, it was rated. Or at least I hope it was rated, because I actually got a... I think I'll probably gain rating. Okay, so let's get started with A. Um, A. So for A, they basically have some coordinate plane, and there's a special tree um, growing at this point. And then the input trees are a bunch of trees somewhere along the, I guess, the positive x-axis. So the input trees are something like this. And then they want you to draw a triangle around three of the trees to create a triangular pasture. And it has to have non-zero area. So because the red trees that I've drawn here are all collinear, we have to include this top tree. So like, here's one example triangle. And area equals 1/2 base times height. Whoa, getting used to my tablet. So basically, when they ask for the number of different areas, we're looking for the number of different base lengths. Um, so I guess I'll go over the code quickly. Whoops. All right, I'll just go over the code in my submission since I made a small mistake. So basically the constraints here are really small, so I just looked at every pair of possible trees, and I inserted the base length that you get from them into a set, and then I printed the number of distinct elements in the set. Um, let's go back to Goodbye 2020. Cool. All right, so let's do B. Um, Okay. Yeah, so let's look at B. And let me know if you have any questions for me in the chat. Awesome to see so many viewers, so okay. So for B, what we want to do is we basically have some array with some numbers, and we can either increase them by 1 or leave them as is. So, and we want to have as many distinct numbers at the end as possible. So let's look at an example. So if we have 1, 2, 2, 2, 5, 6 is the first example. So the trick here is if we go left to right, the input's already sorted, which is convenient. If you go left to right and you increase a value, let me put this another way. If you're going left to right and you've already seen a value, then you should increase it, always. And the reason for that is that it might cause one collision later, but it definitely gives you one fewer collision right now. So what we would do is we would have 1, 2, and then this 2 has already been seen before, so we make it a 3. Then this 2 has already been seen before. Actually, this one, it doesn't matter what we do with it, because we already have a 2 and a 3. But we can just make it a 3. And then this 5 hasn't been seen, so we keep it as a 5. If something hasn't been seen, you don't want to increase it, because if you increased this to a 6, then it might potentially cause a collision later. And then this stays as a 6. So then here the answer would be 5. Let me just quickly read chat. Let's solve this problem. A lot of people are asking if I'm Indian. My ancestry is from India, but I live in the US and I grew up in the US. And in general, let's try to keep the focus on problem solving. Okay, so Yash asked a good question about the solution to A. So I'll get back to that in a minute. So yeah, so for B, let's look at my implementation. So what I basically did is I just kept track of everything we've seen so far, and then if we had already seen something, we increase it by 1, and then we say that we saw the new value. And then at the end, I just deduplicate the items in the array and print the number of distinct elements. Oh, hi Shiwu19. So then, yeah, so actually this is kind of interesting. I got wrong answer on this and took a while to figure it out. So I'll quickly go over that in case it's helpful to other people. So the reason I got wrong answer here is because I just checked if something was equal to the previous element, because I was thinking like, well, it's either going to be equal to the previous element or it's not going to be equal to anything because the array is sorted. But that actually runs into problems when you have an array like 1, 2, 2, 2, 3, where if you do it the way that I incorrectly did it, you get 1, 2, 3, then this isn't equal to 3, so it stays as 2. And then this one is not equal to this 2, so it stays as 3, but it actually should be 4. So that's kind of a funny edge case. It actually took me quite a while to figure that out, I think. Yeah, it took me 9 minutes to figure that mistake out. So yeah, I guess always pays to be careful on the early problems. Okay, so some people asked about this formula, is this only for a right triangle? And the answer is no, it's for any triangle as long as the height here you measure as perpendicular to the base. So that's called the altitude of the triangle. And Genius, living up to their name, said if you get 3 in a row, it breaks your original algorithm. Yeah, that's exactly right. Cool. Let me check. Shibu19 says you can decrease by 1 as well. Yeah, I thought that at first too, so I was going to try to figure out, like, I think if that were the case, you could solve it by decreasing every number as soon as you see it, unless it causes a collision. Okay. Cool. Couldn't you just sort the array and it would solve the problem? So the original array is sorted. The problem is you you would want to sort it after each change that you make, which would be equivalent to like just making a few swaps, but it's definitely easier to just keep track of everything in a set. All right, let's look at, let's see if I'm passing any system tests. Nice, I got A. Someone asked, are we going to play chess today? I think probably no chess today. Already been a pretty exciting day with the contest. Someone asked if I used multi-set, and the answer is no. Okay, so canine poetry. This is actually a pretty tricky problem, I felt. So basically the idea with C is that we want to avoid any palindromes. And the thing that's kind of cool here is, like, if we wanted to avoid... So at first this seems a little bit tricky, because you want to avoid palindrome substrings of any possible length. But here's the trick. If you have a palindrome of, let's say, length 7, it actually contains a palindrome of length 3 inside. And similarly, if you have a palindrome of, let's say, length 6, it contains a palindrome of length 2. So we actually only need to avoid 2, 3 length palindromes. Someone pointed out you can use Heron's formula for problem A. That's pretty cool. I guess you'd have to be careful of floating point error, but should be fine if you are careful about that. Okay, so now that we only have to avoid palindromes of length 2 and length 3, we can actually solve this greedily. And the way that we would do that is we would go through the array from left to right, or go through the string from left to right. And for every value that we see, we check. So every time we see a palindrome of length 2 or a palindrome of length 3, we want to change one of the values to break it, so to speak. And we can always change the second value, or the last character of the palindrome equivalently. And the reason for that is because you might potentially have like a string like this, where you want to change this one, and then you also want to change this one. So it's best to change the one in between. So let me pull up my code. So what I did here is I went through and I checked to see if a given character needed to be changed. And I did that by seeing if it was the second element of a 2-length palindrome or the third element of a 3-length palindrome. And if it was either one of those, then I wanted to change it. And then kind of the cool trick here is it's always possible to change it to something that's that disables all the palindromes after that, but you may not necessarily know what that value is without looking ahead. But because it's always possible, I just changed it to a character that wouldn't be in the string at all. Yeah, so, and then someone pointed out in this example, changing this to ABA wouldn't do much. So what you would do is if you had this string like AAA, you would go through and you would change this A to like a C or a Z or some random letter, and then you would go through and then you would also have to change this A. So in that case, you would still have to change two things. Exactly, yeah. So someone said AA can be converted to A and then two @ signs. Let me just catch up on chat. Is it possible to prove why you will always have a character to replace with? Yes. So the reason it's always possible to have a character to replace with is because I think if you wanted to, you could also look ahead, see what those characters are, and then wait, maybe it's a little bit trickier than that. But if you do look ahead, you can look at the next characters and then figure out what you want to do based on those. But it's just easier to like not do that. There are 26 characters and you're only looking at 6 at a time. Yeah, I think that might be another way to think about it. Cool. All right, let's catch up. Oh, and I think I got a... Oh, and I got a hydrate a little while ago. I missed it, but today I'm hydrating with my lunch. Cool. And I see someone asked again, why only 2 length and 3 length? And the reason for that is that any long palindrome contains either a 2 length palindrome at the center or a 3 length palindrome at the center. Cool. All right, let's do D. All right, so D was kind of an interesting one. It seems pretty complicated for sure. You're drawing a graph, or you're coloring a graph, I think. So honestly, for D, I didn't really prove my answer rigorously. I just kind of intuited that it was probably right. Okay. D is pretty easy after the wall of text. Okay, cool. So basically my thoughts for D, which I think we're on the right track, is let's imagine you have like some tree, right? I'm just kind of drawing a random tree here. And the idea that I had was, this is a pretty complicated definition, but basically here, the value of a subgraph is the maximum of values of its connected components. So you kind of never want to have a disconnected subgraph, because if you have a disconnected subgraph, you're basically not going to be getting any value out of the like the smaller component. So you could have just added that smaller component onto another subgraph instead. So then what we want to do is think about it this way. So let's try highlighter. So let's say we do something like this. That's kind of weird. Okay. So let's say we do something like this. Then we can look at how many times each value gets counted. So this one, oops. This one is part of the green graph. This one's part of the green graph, green. This one's part of both graphs, and these are only part of the red graph. So basically what we want to do is we want to consider the contribution of a single vertex. And the contribution of a single vertex is the number of different colored edges it's incident to, or that are incident to it. So in that case, we can look at the code. So you actually don't even need the structure of the graph, you just need the degrees of every vertex. Yeah, cool. So what you do is you just start with the vertices with the largest weight, because those are the ones that you want to double count or triple count. So, and then you just want to greedily add extra colors to each of those. So your initial score is the sum of all the vertices, because you just have like one giant component or one giant subgraph. And then what you do is you loop through all the vertices starting from the largest, and whenever a vertex runs out of extra edges that you can add to it, you go to the next vertex, and then you double count, or you count one extra time the vertex that you're at, and then you decrease the number of available spots it has. So cool. So that's D. 20 pixels says so simple, and GT Matters says I used priority queue. Yeah, so you could also use a priority queue. The kind of cool thing, right, is the order will never change because it's just based on the original weights. So you can use a priority queue or just a sorted list. A priority queue is kind of cool because you can just pop the front element instead of having to use an iterator or an index. And yeah, this was a surprisingly simple problem after like this very messy looking definition. Cool. Someone asked, what's your complexity for D? So I sorted the vertices, which would be n log n. And then other than that, I just loop through stuff, so that would be n. So I guess it was O of n log n total. Cool. So that's D. All right. Now, E was actually, I found like super difficult. So we're already getting to the very tough problems here. So let's see. Actually, I'll grab my paper. Cool. So E has this extremely scary looking sum. Cool. So someone highlighted their message and said, "Can you go back to B?" No, but you can watch. So you can rewind back to B yourself, I think, by going to my videos page on Twitch and looking at this broadcast and like rewinding. Cool. So yeah, I don't have a link to it. I guess I can add that. Cool. So hopefully that works, and then later you can always follow me on YouTube, and I'll upload this there as well, so it should be easy to watch there. Cool. So yeah, so as people are saying in the chat, the intended solution is O of 60 times n. I actually spent a long time coming up with this O of 60 squared times n, because I just kind of thought, oh, well, 60 is a small constant, it'll be fine. And then I realized later that this would not work, and I had to basically start over. um, but yeah, so let's go over this. So let's see, should I go over the wrong solution first, or just skip to the right solution? What do people think? They were pretty different. Well, they had a bit of the same idea, right? Because they both have a factor of 60. All right, people are saying wrong first. Awesome. Oh, and wrong so I can feel at home. Awesome. Cool. So let's try to figure this out. Okay, so let's let u equal xi and xj, and v equal xi or, oh, whoops, it's xj or xk. Um, Whoops. Yeah, I'll just make this a little bigger. Cool. So the trick here is you want to write u as the sum of like some powers of 2. Like maybe it's 2 to the 0 plus 2 to the 2 plus 2 to the... whoops. 2 to the 3. And then like v might be the sum of some other powers of 2, like 2 to the 1 plus 2 to the 4. And so for every pair of powers of 2, can you please explain what the problem is as well? So for the problem, so here's the link. But I'll quickly explain the problem. Basically, you're given an array of n numbers, and you want to look through all triples of numbers, including repeats, and you want to find this weird bitwise operation, and then you want to sum that over all the triples. So the obvious way to do it would be n cubed time, which is definitely too slow, and our target is something more along the lines of... yeah, and just a quick note, just use English in the chat, because otherwise I have no idea what you're saying. Thanks. So, yeah, basically what we want is some sort of linear solution, because n here is, like, really big. Oh, that's really kind. I actually do understand a couple of those words, I guess. Okay. Anyways, so what we want to do here is when we multiply u times v, we're basically like, this is like the distributive property. We're picking one element from u and one element from v and multiplying them. Oh, what's the Google translation? If someone could paste it here. Alright, I don't want to click that. Okay, so what we want to do here is we want to consider some term that's 2 to the L times 2 to the R, just for left and right. And we want to count how many times this appears. Oh, that's funny. Alright, please don't ask me to ban other people. Oh, I guess... yeah, okay. Anyways, So we want to count how many times a given pair of powers of 2 would appear. So a cool way to do that is to consider random I, j, k. Find probability that 2 to the L times 2 to the R appears. And let me add a link to the Jamboard in the chat. That way if I go back to the preview, or if I go to the next slide, then other people can look at the previous slide. Cool. So I'm just gonna go to the next slide, but I don't want people to be completely lost. So you should be able to open that yourself and scroll to previous slides. So the way that you end up finding the probability that L appears in the left would be you need xi to contain L, and you need xj to contain L. And then for R to appear on the right, you need x and or. Cool. So now I guess I'll switch over to the code. So what I did here is I split this into 2 cases, and I guess I used U and V instead of L and R here, but I think that's fine. So first you have the case where U and V are equal. So in order for that to be the case, you need I don't know why I wrote this. Okay. This should actually be the same as count U or something. So basically what we're doing here is we're finding the probability. So xi needs to contain U, and then xj also needs to contain U. So the probability of that is count of U, where that's the number of elements that have that bit set, just with this pre-processing, divided by n, and then squared. And then if U and V are different, then we kind of have a couple cases. So first, we definitely need xi to contain U. And then we also need xj to contain both U and V. Or we just need xj to contain U and xk to contain V. And then we have to subtract out what we double counted. So that's principle of inclusion-exclusion. So now we calculate the contribution to the final answer, which is 2 to the U times 2 to the V times the probability. And here, answer is the expected value of the sum for a randomly selected triple. So then we want to multiply that by n cubed. And actually, this code is wrong because n cubed here will overflow since n is an int before it turns into a mod num. So this would be correct. So this is the slow solution, and the problem is this pre-processing step. I couldn't figure out how to do this any faster than 60 squared. Z here is 60. 60 squared times n. And I believe that would TLE because that would be around like a billion operations. Maybe you could squeeze it in. It seems like some people in the chat are saying that they passed pretests, which is pretty cool. Great. So now somebody in the chat said fix J. So that's exactly right. So now we're going to go into the fast solution. Whoops. So we're still doing E, right? Yeah. So E fast. So here we want to be able to solve this without computing that count for all the pairs. We just want to be able to do this in 60 times n. Cool. So there's kind of a cool trick to this. So first we can interchange the summation. So let's put j on the outside. Then okay. So now let's define some function f sub j of uv equals to like this inner term. So this summation is the sum over j of, wait. Yeah, okay. So this summation is the sum over I and k of f sub j xi xk. And kind of the cool thing here is if you look at this term and this term, and you treat j as like a fixed value, like a constant, and you're randomly selecting I and k, then these two terms are independent. And we know that the expectation of xy equals the expectation of x times the expectation of y if x and y are independent. So what we want to do here is we want to find the expected value of this stuff inside for any fixed value of j. And we can do that by finding, let me rewrite this sum a little bit. So we can solve this like this now. Using this independence property over here. So the cool thing is now we just need to find this and this separately. So we've separated the and stuff and the or stuff, which is nice because they were kind of complicated before. Cool. So now let's look at the code. Cool. So what we're doing here is you can see we're only pre-calculating these in 60 times n time because we're just counting the number of each individual bit. And then and then what we're doing is for each value of xj, we're calculating the expected value of this left term and the expected value of this right term. So for the left term, we go through each bit, and um, we're gonna add a 2 to the u only if the youth bit is in xj and in xi, whatever that is. And then for the right term, which is the ors, we're going to do it if it's either in j, xj, or if it's in xi. And then we have left times right, which is the inside of this summation over j. And now that we've added those up, we find the answer if we randomly selected I and k. Oh, Jack Silv, thanks for the subscription. Yeah, if you have Twitch Prime, you can subscribe for free, which is pretty cool. Cool. So, and then we want to multiply by n squared because we found the expected value if you randomly select I and k. And so now we want to find the sum over all choices of I and k. Cool. So that's E. And then here I actually got wrong answer earlier because I made this mistake. Pretty easy to make, but so n here is an int, so n times n would overflow before you multiply into ants, and then a lot of these other things are mod nums, so you don't have to worry about that. But cool. So that's E. Wow, it looks like I solved A, B, and C. That's awesome. Can you brief this once again, please? Yeah, so you can always go back in the current video, and you can always go back in the whiteboard with a rewind or Jamboard command. Yeah, and and someone asked, will the VOD be up later? So I'll upload the VOD within like 24 to 48 hours on YouTube. So you can subscribe to me there as well. All right, so F, Euclid's Nightmare. So I actually found F a lot easier than E, which was kind of interesting. Probably because I did E the wrong way first and then like started over. But so for F, you basically have a bunch of vectors modulo 2, and you want to find the minimum size of the basis, which I think is like the rank of the vector space, and then you want to compute the number of different vectors you can get. And so each vector, you can either include it or not include it if you have a bunch of linearly independent vectors. So this value, the size of t, is always going to be equal to 2 to the s prime. So if you look at the samples, you can actually see this, right? 4 is 2 squared, 8 is 2 to the third. Is the rewind link correct? Good question. Yeah, so you can find my past broadcast here. It's like it's the video without a thumbnail with the current title. Cool. And yeah, if you have questions about previous problems, maybe I'll cover some at the end, but for the most part, I think the questions are explained if you just rewind to that part of the video. All right, so let's forge ahead with F. And let's look at one of the examples. F. All right, so for F, we have, let's try an example. We have a 1, and then we have a 2. Whoops. Then we have a 2, and then we have another one that contains a 2 and a 1. So let's write that as 1, 2. And then it turns out here that if you just take the 1 and the 2, you can generate this from it. So the answer would just be this one and this one. So there's actually a cool trick to this. First, let's consider the case where all the vectors have 2 1s. Since actually I think that turns out to be a bit simpler. So what we can do is we can number all the dimensions from 1 through m. And then we can consider this. Like, let's say we have a 1, 3, and then we have like a 3, 4. If we combine these, we end up getting a 1, 4. So this kind of leads us to this intuition that we can consider the vectors as like connecting two of these dimensions together. So then like a 1, 4 would end up being redundant. So in this case, the answer is pretty simple. You can just loop through the vectors, and then when you find... Well, so I guess to rewind a little bit, since maybe I should clarify this. So they want you to find the minimum size basis, and they also want you to find the lexicographically smallest basis, which means that you can go left to right in the input, or I guess beginning to end in the input. And whenever you get something that's linearly independent from the previous things, you add it to your basis. And if it's linearly dependent, you ignore it and you move on. So in this example, we have 1, 3, and then we have 3, 4, and then that's new. And then we have 1, 4, which is not useful. So the answer would just be these two. So the trick is you want to be able to do this efficiently. And so it turns out you can do this efficiently using a union find. So what we do is if we have two things that are connected, then, well, basically what we do is once we get a vector that has 2 dimensions with 1s in them, we connect those 2 points in the union find. And if this actually created new connectivity in the graph, this means the vector is linearly independent from the previous ones. So let me open my code for this so that people can kind of understand what that would look like. So super simple. What we're doing here is for each vector, we connect the 2 1s. And then if that actually added new connectivity to the graph, we use that vector. Now the problem is, how do we deal with vectors that only have a single 1 instead of 2 1s? And it turns out that you can add a dummy dimension. So I just called that dimension 0. And you can replace all of these with like a 1, 0 and a 2, 0. So like, if we took this example from the input, you have 0, 1, 2, and then first you connect 0 and 1, then you connect 0 and 2, and now everything is connected. So when you try to connect 1 and 2, you don't actually like accomplish anything new. So 1 and 2 is redundant. Nice. Got another hydrate. This is great because I'm having my lunch. So if we look at this in code, what I did was basically, this is kind of like clumsily written, but basically what I did is if something was a single element, I just added a 0 to it. And then I just went with the same solution as before. And then here we can see at the end that the size of t is just 2 to the size of s prime. And then this is s prime, and then you print the values in s prime. Cool. So that's f. Definitely my solution was a little bit hand-wavy on the details, so maybe let's see if we can formalize them or explain them a little bit better. I was actually a little skeptical of this when I thought of it because I found this a lot easier than I found E. So I was wondering if I like had missed something or like some tricky edge case. So, all right. So let's see. So basically the idea, right, is you consider okay, so here's one way to think about it. Let's say you have a bunch of vectors that you use and they don't have anything in common. In that case, it doesn't matter what order you kind of add them to your current vector when you're building up a vector. Um, so we can kind of just add them completely separately. They're definitely independent if they don't have any terms in common. And then if they do have terms in common, then it's always possible to add them in such a way that you're always adding something where one of the elements is equal to one of the elements of the previous thing. So if you always are adding stuff that has something in common, um, you can kind of like add them in like this order. And then you can kind of clearly see that this ends up with you getting from 1 to just 1 and 4. And I think that kind of shows a bit more of the intuition behind this union find solution. And then you might worry that by adding a 0th dimension, you're kind of over or under counting stuff. But I think the reason that you're not is because all the vectors have parity 2, except for the single element vectors. And the single element vectors, the number of those that you incorporate in the vector you're building determines the parity of the vector you're building. So as a result, for any given vector you built, there's only one possible value of the dummy 0 dimension that we add, which means that you're not going to be counting wrong, basically. All right. So let's go over what's going on. System testing is having some issues. I don't know. Nice. I got A, B, and C. Did any of my stuff fail sys tests? I guess I don't know how to tell. It's all in queue. All right. So let's go over G. And so for G, I did a hashing solution. I actually just learned how to do string hashing problems like yesterday or the day before. So this was super fortuitous for me, or maybe that's the wrong word. It's super lucky for me. But I'll just write hashing. So if people have a non-hashing solution, that would be pretty cool. And hopefully nobody hacks my hashing solution. But you never know, I guess. So basically what we're doing here, what was your in-contest intuition behind adding the dummy dimension? That's a great question. Let me actually see what I wrote on this paper. Oh no, you just gave 130 people that idea. Yeah, I don't really know. I just thought of it. Maybe I got kind of lucky in this problem because I just randomly thought of a trick that works without any super clear motivation. But yeah, I mean, I'm like looking at my paper and it's like I just have like this is what I did for F. It's not really that exciting, I guess. So All right, so let's do G. So the thing with G here is that actually building up the string S could be like huge. Like it could be like a 2 to the 1 million, or no, maybe 2 to the 100,000 or something in length. Um, oh, Gecko says, do you think it's possible to solve G by hashing all the sailor names, then hashing substrings of the ends of each of the end songs, and then comparing hashes to queries? I think that's basically what I did. Um, but yeah, let's go over this. Okay, so the main trick to this problem that I found is, so we don't want to compute SK, right? SK too big. But let's find S small such that S small is still longer than W. So this is how we're going to solve a given query. So the reason that this is useful is that now we know that our SK is going to be equal to S. Let's actually just call this S from now on. Yeah, so SK is going to be like S times like some character, or concatenate some character, then S, then some character, then S, then some character, and then so on. And because we know that S is longer than W, we're always going to have either W in S, or, I don't know why I wrote that. Or we're going to have something like, this is S, this is some character, and then this is S. And then, like, this would be W. But, awesome. Some of my loyal subscribers are using my custom emote. You can also use that in any other channel, I'm pretty sure, though I'm not totally sure how Twitch works. If you ever wanted to. Okay, so the cool thing here is because S is larger than W, we're not going to have a situation where you have something complicated like this, and then W is like here. So I think this might be along the lines of what Gecko mentioned in the chat. So, all right, so now let's actually just look at the code. Or I guess maybe first I'll describe this a little bit more. So you can count W being inside of S once you've built up S by using string hashing to get any substring of S's hash and just checking every appropriate length substring to see if it matches W. And then what you're going to want to do is that's going to end up contributing something like this copies to the final answer. And then we also want to count the number of ways to have this thing where we have one of the in-between characters here. And the way that you can do that is, again, using string hashing. You have a suffix of S and a prefix of S, and then you want to join them with some other character in between and have this be equal to W. And then that will show up however many times, like, so you keep expanding your string via your process, and then you'll reach a time where you add this mystery character, this in-between character, and then however many times you double your string after that is how much contribution this one gives you. And the last kind of cool trick is now we know that the size of S small is at most twice the size of W, since we basically double it over and over until it's at least the size of W. So all of this hashing time ends up being something like the total length of the sailors' names plus, and then I actually built in an edge case for when you just have S0, because I think you could have just S0, which is length 100, and then have a ton of sailors of length 1 and then hash that over and over, but you basically just hash S0 once at the beginning, just in case. Cool. So now let's look at the code. It's a little messy, but I have some local benchmarking. So this stuff you don't really need to know. It's just some pre-calculation. I'm using this great string hashing library from Socket. Okay. So let's go down to the main part of the problem. All right, so here we have a query. So what we do is first we find all the pre-computation we need to be able to hash W. And then we start building up our string until it's at least as big as W, which enables us to have this kind of simple logic later. And then we count how many iterations we used up because we're going to have to use some iterations later. I guess I can clean up my code as I go so that it's easier for people to read as I go. Cool. So I think one of these is probably unnecessary. I just added them because I got wrong answer. But basically there's like some edge case here where it's not possible to make S larger than W, even if you use all K iterations, in which case the answer would just be 0. And then this code is actually written a little bit awkwardly where small... If K equals 0, you'll never actually hit this. So I guess this could have been written as something like this. And that would have been cleaner and saved me a wrong answer. But basically these are like edge cases where the answer is just 0, so we move on. Then what we want to do is we want to get all the prefixes so we can do string hashing on S. And then, so here we find the count. So as we saw here, we want to count how many times W appears directly in S. So what we do there is we just go through every possible offset and we just check to see if the hashes match. So that's how we do that. And then this is kind of the more tricky part. Someone says, where can I find that library? So I have my version, and then Socket has the OG version. And I've just made a couple small changes to it, so like you can probably just use his. And it's called AlgoLib on GitHub. So now what we want to do is we want to count each possible in-between character. And so what we want to do is we want to consider some offset of W. So I here is going to be the number of letters to the left of the in-between character. So then the in-between character will be WI. So here we're just checking to see if we offset S and do this. So this is the suffix of S, and this is the prefix of S, and then this is the in-between character. If that hash matches, and then we're saying that for that in-between character, yes, it did match with that offset of W. So then what we do is we want to count how many times the in-between character appears. So what we do is we could loop from I equals small up to K and check to see for whatever in-between character we're using there, which is T sub I, or T sub I minus 1, depending on your indexing. You would do this count for the in-between characters, and then you would multiply by 2 to the K minus I, because that's how many iterations there will be after this. You can see this is the contribution from when we don't use an in-between character. But in order to do this efficiently, instead of looping through Because if I looped through... Actually... Yeah, okay, so we can't loop all the way up to k. The reason for this is we can't loop all the way up to k because k could be 10 to the 5th. And then if we did that, this would end up being q times k runtime, which would be too slow. So what we do here is we actually have this kind of clever trick of pre-computing 2 to the minus I summed over all the values of the in-between character. So that's the pre-computation that we did up here. And then we just multiply by that. And for a while here, I was getting time limit exceeded because I had a 26 times 1 million solution, which I guess was just a little bit too slow. And the reason for that is that I looped through all possible values of the in-between character before I realized that. So here I looped over the alphabet size and over the length of W. And it turns out that you know that the answer will be false unless this is true, so you can just set it to that. Yeah, so that's why I got some time limit exceeded on G. Because initially I had this loop where you loop over all the possible in-between characters. And then I think some people did it in time 26 times 1 million, which is not what I did. So I'm kind of curious how that didn't TLE. Maybe it's because hashing has like a bad constant factor. Cool. So that concludes my explanations of A through G. I'm thinking I'll go through the editorial and see how they did A through G, and then say if there's any like key differences. And also, yeah, I'm happy to take some questions if people have them. So someone asked about E. Is it necessary to use expected value and multiply by n inverse? So I find it a lot easier when you're doing these complicated summations to find the expected value of like one kind of thing and then multiply by the total number of things. Whoops, I think I messed it up. Yeah, okay, cool. And then multiply it by the total number of things. You could also instead look at this and then think about how many values of k you could have and multiply by n here, and I think n here, and then not do this. But I personally find it easier to separate them. So I just calculate this like simple expected value, and then at the end I multiply by the other stuff. Yeah, I think it's just a little bit simpler that way. Cool. So let's look at how they did these problems. All right, they iterate over everything. All right, so they did the greedy solution that we did, and then they have some... I see. So yeah, so they kind of looked at the... so you would have to take out the n inverse, and then... You'd have to take out n inverse and add times n. So, I mean, it's basically the same, right? If you just think about it algebraically, you're just multiplying you're just distributing the times n into the inside of the for loop. All right, so, okay, cool. So they also did this 2 and 3 thing. Yes, they did the same greedy thing here. All right, so they did some rewriting. But yeah, it looks like they did it basically the same way. They fixed xj. Let's see how they implemented it. Cool. Yeah, so this is an example. They do times n here instead of on the end. All right, so here they added an additional dimension. Now they're saying it's intuitive to create a graph. Okay, so I guess that's another answer to the question that someone asked earlier of how do you come up with adding these extra definition? It's that, or this extra dimension. It's because you almost have a bunch of things with two elements, which is natural to combine into a graph, but you don't quite. So why not try to make it so, right? Cool. All right, so let's read about G. Cool. Um, all right, so it looks like they did the same thing here, where you try to increase S until it's larger than W. Okay, and then they had this recurrence. Okay, so this is just finding the number of substrings. Okay, so instead of hashing, you could just use KMP or Z algorithm or like any kind of standard string algorithm to figure this problem out. The W in S, right? That's a simple counting substrings thing. And then for the second thing, cool. Okay, so my solution works in this runtime, and it was needed to get accepted for me. Um, but apparently, if you were more efficient, you could do it with this extra alphabet size term thrown in. So what they did is contain character t n minus 1. Hmm. One second. Okay, so it seems like this is basically the same as what we did. But I'm a little confused about this phrasing of if it contains character tn minus 1. I guess they mean if it contains... Oh, I see. Okay, yeah. I think that is what they're saying. I see, yeah. So I guess for the character that you just added... Okay, I think they mean with the exact character you just added, not just like that character appearing somewhere. What are A and B? I actually don't even... What? Oh, maybe they just mean by adding something. Okay, it seems like what they ended up doing was very similar to what I did, but maybe phrased a little differently, and then they used KMP instead of hashing, which I guess gives you a better constant factor. Um, awesome. So I guess that kind of wraps up this contest. I'm not going to spoil H and I. And system testing is 70% done. Um, cool. All right. Oh, and I got another hydrate, so I'll enjoy my lunch. Cool. So yeah, that basically wraps up this contest. Someone said, "What's next in educational content?" Oh, and I should have said this before, but I also have a Discord. So feel free to join the Discord. It's basically just gonna be like maybe me asking people for feedback or basically another way to stay up to date on what I'm gonna do next. I'll post announcements there. I think right now it's pretty empty. Oh, Hydrate says make me take a sip of water. So it's chocolate flavored Soylent. Um, Normally I would have water, but so right now it's like 2 p.m. Basically the contest ended right around lunchtime. So I'm having that so I'm not hungry. I mean it's harder to drink than water, I guess, and it's equally hydrating. And then Jake says, "Thank you for not spoiling H and I." Yeah, you're welcome. I mind solved them during this stream, but I didn't want to give them away because I don't have the code prepared. So okay, and then someone said, "What's next in educational content?" So what I think is next is there's an @coder contest coming up on Saturday or maybe Sunday, depending on your time zone. So I'm going to participate in this @coder contest, and then I'll do a post-contest discussion of that. So that should be pretty fun. I think it's, yeah. So that'll be my next stream, most likely. And then I also have a combinatorics and expected value topic-based problem set and stream kind of in the works, but that might be a while. So yeah, let me know if you have any other questions. If not, I'll probably end the stream pretty soon. Thanks, everyone. And then I just posted a couple links so you can try to keep up with what I'm doing. But yeah, and I hope these pass. All right, thanks everyone. Cool. So I'll end the stream now, and feel free to reach out via Discord in the server. Bye everyone.